Okay, this is going to be an introduction to spectrum analyzers. Unfortunately, the spectrum analyzer has a fan in it, so it turns out that this might be noisy. Hopefully I'll be able to speak loud enough over that fan. This is a Keysight CXA signal analyzer, aka spectrum analyzer. Goes from 9 kilohertz to 26.5 gigahertz, and basically what it is a radio receiver, and you can tune that wide range of frequencies, over 26 gigahertz worth of frequency, with this single receiver. What it does is it displays signals in what's called the frequency domain. An oscilloscope, on the other hand, shows how signals vary with time. We call that a time domain display. The spectrum analyzer shows what frequencies are present and their amplitudes. Another interesting thing about the spectrum analyzer, unlike the oscilloscope where the ground level is in the center of the screen, nominally, on the spectrum analyzer, the reference is at the top of the screen. Right now, the reference, or the very top of the screen, says 0.00 dBm. It says the center frequency is 13.255 gigahertz, and resolution, bandwidth, 3 megahertz, span of 26.46 gigahertz, and there's 1001 points that show this display. So what I've got is I've got a signal generator, which I will take and turn on. And when I do turn it on, hopefully I won't kick the tripod anymore, but I'll turn on the signal generator. Looks like I've got to take and replug that in. As the signal generator comes up to power, I'm going to take and apply the signal generator's output to the spectrum analyzer. You can see that over here. Spectrum analyzers typically have an N connection, so I've got a BNC to N adapter. It takes a little while for the signal generator to come up. When it does, I'm going to take and set its frequency to 1 megahertz with, say, about a 1 volt peak-to-peak sine wave coming out of the signal generator. So while I do that, let's see what happens on the spectrum analyzer. Okay, now, on the spectrum analyzer you don't see anything occurring. So what happens is right now the spectrum analyzer is at full span. It's looking at this big wide frequency spectrum, and it turns out that the 1 megahertz signal is buried in everything else. So, a couple things I could do. The spectrum analyzer has an auto tune feature, so let's try that in the top right hand corner here. I'll hit the auto tune, and turns out, oh, we have one more problem. There's no output from the signal generator yet. So let me turn the signal generator on, and then I'll hit auto tune, and still nothing. So it turns out that obviously we don't have enough power or sensitivity to see that signal yet. So what I'll do is I'll go over to the frequency controls, and I'll set the start frequency to, say, 0 megahertz. And I'll set the stop frequency to, say, 50 megahertz. And lo and behold, over on the far left hand side we see something that appears like a signal, but it's way over to the far left hand side, not of much use to us. So what I might do is think to myself, well, if it's a 1 megahertz signal, maybe what I should do is take and set the center frequency for 1 megahertz. I could do that if I set the start for 0 and the stop for 2 megahertz. So let's go back to the stop, and we'll set that for 2 megahertz. And lo and behold, we see a signal in the center. Okay, now it turns out that the signal we see in the center goes up and it exceeds the top reference, so it's probably more than 0 dBm. So I have another control over here, the amplitude I could set, and so I'll click on amplitude. I'll make the reference level say 10 dBm, and lo and behold, there's our signal. Now there's always, with spectrum analyzers, an artifact called zero or DC feed through, and on the far left hand side you see what appears to be a signal. There's no signal there, that's just an artifact of the spectrum analyzer. Every RF analyzer has that artifact, and you can't get rid of it. Now, it turns out that what I might want to do is make sure this is my signal, so maybe I'll go over to the marker over to the right hand side here, and I click on the marker, and I'll do a peak search on the marker, and it tells me that, oh, it's 1 megahertz signal. Matter of fact, you take a look up in the top left hand, it says marker, looks like 1 point followed by about 20 zeros. It's only about 10 zeros, but quite accurate to say the least, I guess. The other thing it tells us is that the power is 3.97 dBm. I'll be the first one to caution you that spectrum analyzers were never made to be extremely accurate with power measurements. They're pretty close, but they're probably, you know, anywhere, it could be a half dB or off from what the exact value is. Right now, the reference is a scale of dBm. I could actually take, and let's go back to amplitude here, and there are basically 3 buttons over here that are the key buttons of let me zoom in on them a little bit. These 3 buttons up here: frequency, span, and amplitude. Those are the ones that you tend to use most of the time when you're playing with a spectrum analyzer. So if I go back to the amplitude, well, let's go to scale, I guess, if I can find the scale. And I'm looking around and I don't see it right away, so I'll go and do preset. Then I'll go back to start frequency of 0 and stop frequency of 2 megahertz. Okay, then I'll take my scale type, and down the bottom here, if I go linear like that, it turns out my, a log on the frequency, it turns out I set up like a Bode chart, a logarithmic scale. The vertical scale is logarithmic. So I'll get rid of that. Scale type, go back to linear. If I go to amplitude, scale type, I can go to linear here. And now what happens is, notice the reference went to 2223.6 millivolts. That's RMS. When I might have to set the reference level to, say, 1 volt. And now what happens when I go back to my marker and I do my peak search, I see that I have, well, here's an interesting 353 point whatever millivolts. Of course, that's RMS. So what happens is my signal generator is putting out a 1 volt peak-to-peak signal, so the spectrum analyzer is calibrated in RMS as opposed to volts peak-to-peak. And of course, to get power in dBm, you have to take the RMS voltage, not the peak-to-peak voltage. So the factor there is 2 times the square root of 2. So if I divide 1 by 2 times the square root of 2, I'll get 353 millivolts roughly. I don't see any other controls where I can take. If I go back to amplitude, I got more over here. No, it just turns out that all I could do is do it linearly, and it's got to be in, well, let's hit the reference level. 1 volt, and no, there's no way to set it for anything else but RMS. Okay, let's go back to a logarithmic scale, and it turns out that 1 volt peak to peak is about 4 dBm. That would be the power. Okay, so this doesn't show us too much except the fact that we can take and see a signal. If I go up to the signal generator and hit frequency here and change the frequency, we can see what happens is it will go and move around the display. So what we're doing again is we have a very sensitive radio receiver that can tune a very, very wide bandwidth of frequencies, and it turns out it displays that signal, and it also displays a lot of noise there, to say the least. If I take and look over to my other controls here, let's see, I'm looking for bandwidth or view display, maybe mode setup. Measurement setup, average. So if I do averaging, and I do manual averaging, which is not letting me power average, not seeing too much here, so I'm gonna get out of there. If you average, you can get rid of the noise, but my familiarity with the spectrum analyzer is limited at this point in time. I usually play with the older ones. So let's just take and say for the time being that we could average the signal, and then the noise would decrease a little bit. It wouldn't be bouncing up as much as it is. So let's go and change the output frequency from the signal generator to 10 megahertz. Let's see what happens. So you notice that what's happened, the signal's disappeared off the scale. So 10 megahertz, I can try again auto tune. Let's see what happens with 10 megahertz. If I go back to, if I do auto tune, it turns out that a marker appears over on the far left hand side, and it looks like the frequency is 10 megahertz. And if I take in, let's see what I can do here. Set my center frequency to exactly 10 megahertz, brings it back into the middle of the screen. So you notice that the dB value now is 4.06, a little bit higher than it was before. Reference is at 14 dBm. Also, it turns out that if you take a look at the scale, on the left hand side, the scale looks like it's I'm not too sure if it's just 12 dB per division. So if I go to amplitude and scale, I can make it 10 dB per division, and notice that it starts up at 14 dBm, so the first one down is at 4, minus 6, minus 16, and so forth. You can play with the scales quite easily with a device like this. Now, what a spectrum analyzer is good for is seeing numerous signals together. And what's happening here is we're only looking at one signal. So what I'm going to do is change the frequency that I'm looking at. And I'm going to do my start frequency at 0 megahertz. And I'm going to do a stop frequency at 100 megahertz. And, well, I don't see anything else. But I'm going to do something. I'm going to change the signal generator to put out a square wave instead of a sine wave. And when I do that, you might notice that what happens is I have many more signals on the screen. Now, hopefully, either in class or someplace, you've heard that what happens is a square wave actually consists of a bunch of sine waves, and in particular they are the fundamental frequency and the odd harmonics of those sine waves. So now here we see a couple other signals. So if I go back to marker and I do, let's see, peak search for the next peak, I get a marker on 30 megahertz, the third harmonic. I'll do the next peak, 50 megahertz, the fifth harmonic. The next peak, 70 megahertz, the next harmonic. Next peak, 90 megahertz. And if I actually increase the span of my spectrum analyzer, I would see that I have odd harmonics that go out infinitely. And of course, by going out infinitely, it's hard to say where they stop, but as soon as they get to be about the amplitude of the noise, then we'd have trouble measuring, to say the least. So a spectrum analyzer, again, now is showing us all within range here of 0 to 100 megahertz, the odd harmonics of a 10 megahertz square wave. Let's change the waveform to something different. I made it into a ramp, and what's happened, the ramp tends to be at a lower frequency. It turns out that ramps can't be 10 megahertz on the signal generator, so I'm going to take and change the frequency of the ramp down to 100 kilohertz, and then I'm going to take and change my start frequency is at 0, but let's make my stop frequency, let's make it 5 megahertz. And here you can see all the harmonics. Let's change the stop frequency to be, we're still activated here, let's make it 1 megahertz, and we separate them out. And here now we see the fundamental frequency of that ramp. The ramp's frequency is listed as 100 kilohertz on the signal generator, so we're seeing a signal at 100, 300, 500, and so forth. If I go and do my peak search with my marker, peak search, there's the, well, it says 99 kilohertz, close enough. Let's go to the next peak, right, and we got to play with it a little bit. 199, let's just try next peak. I gotta go next peak right, and there's 99. If I do this again, we'll get probably 299. Well, now it's 300. And here's 5. Oh, marker at 400 kilohertz. So what it appears to be that I have actually not the odd harmonics now, but I've got the all harmonics. So this triangular waveform, in this case this waveform up here, and I'll zip up with my, that waveform ramp gives me all harmonics. I think if I change the ramp to a sawtooth, and let's see how I do that. Symmetry, let's try 100%. Nope. Here we go. I just changed it to a ramp that it's more like a triangular waveform, and what you can see is now that I only have odd harmonics. So it turns out that the spectrum analyzer is a great instrument for seeing what is there. In this case, it turns out that the peaks go down more rapidly. Triangular waveform has a little bit different characteristic of what the harmonics are in it versus a square wave. So I haven't really shown you everything, but let me show you one more thing, and that is the selectivity of the spectrum analyzer. So what I'm going to do is I'm going to change the waveform out of the signal generator to a modulated waveform. So give me a second. Okay, what I've done is I'll zoom up with my little handy camera here. I've made a modulated waveform. 2 megahertz is its center frequency, and let's see if we can find it on the spectrum analyzer. So what I'll do, as I'm typically want to do, I'll set my frequency to start and stop. Since it's centered at 2 megahertz, let me make my stop frequency 4 megahertz. And what I see is this waveform now, and now you might notice that it's not very stable. I'll put a marker on it, or at least try to put a marker on it, and it bounces up and down all over the place. So what the problem is I'm not really centered in on the signal and find enough detail. So what I'm going to do is there's a span button over on the right hand side here, but I like to use the frequency button. So the start frequency, I'm going to click on that, and I'm going to say, okay, let's start at 1.5 megahertz, and let's stop at 2.5 megahertz. Now we're only showing a 1 megahertz span. You might notice that the frequency of interest is bopping up and down like nobody's business, but it turns out that it's slowed down a little bit. I actually still need some finer detail. Now there's a span button. I could hit the span button and set the span button to like 50 kilohertz. And if I do that, I still see this kind of bunch of gyrations occurring with the center signal. So let me go to frequency again. I'm going to do my start frequency at 1.95 megahertz. And I'll do a stop frequency at 2.1 megahertz. And I still don't really have too much of a good waveform to look at. So let's see what I can do to take in. Got to go back to my signal generator, and what the problem is my frequency of my signal generator. We've got internal, and what I need to do is take and change some of the things with the signal generator. So I'm just going to take and kill